Something appeared in the Martian sky on October 2nd that shouldn't exist. An amateur astrophotographer scrolling through NASA's raw image files noticed it first. A streak moving impossibly fast across the darkness, cutting through the stars at speeds that made our fastest spacecraft look like they were standing still. But that was just the beginning. Within hours, other observers claimed they saw not one object, but multiple. And then someone spotted the green flash, a mysterious luminosity that appeared for just 3 seconds, glowing with a color this object has absolutely no right to produce. NASA had scheduled this observation months in advance. Multiple Mars orbiters, equipped with cameras capable of capturing details as small as 30 centimeters, were all pointed at this visitor during its closest approach to the red planet. These were supposed to be the most detailed images of an interstellar object ever captured in human history. And then silence. No official images released. No data shared. Nothing but an eerie quiet from space agencies on both sides of the Atlantic. Meanwhile, a team at Harvard just published something that's making the entire astronomical community deeply uncomfortable. This object, this thing called 3I/Atlas, might have been responsible for the most famous unexplained signal in the history of radio astronomy, the WOW signal from 1977. The mathematical probability of that being a coincidence? Less than 1%. But the WOW signal connection is only the beginning of this mystery. Because 3I/Atlas is systematically violating every single rule we have for how comets behave. It's producing industrial-grade metal alloys in the vacuum of space. This tail is pointing in the wrong direction. Actually, it has no tail at all, just a strange forward jet. It's glowing bright green when the molecules that create green light in comets are almost completely absent. Its chemistry is inverted, with 8 times more carbon dioxide than water when every other comet we've studied is dominated by water ice. And its trajectory is so perfectly aligned with multiple planets in our solar system that the odds are, quite literally, astronomical. Some scientists are calling it the largest interstellar object ever detected. Others are calling it impossible. And one prominent astrophysicist at Harvard is using a word that makes most astronomers extremely uncomfortable. He's calling it potentially artificial. Right now, as I'm speaking to you, 3I/Atlas is disappearing behind the sun where we cannot observe it. It's hidden, approaching its closest point to our star, experiencing maximum solar heating and radiation. When it emerges in late November or early December, we'll finally see what it's been doing during this blackout period. Will it look the same? Will it be following the trajectory that gravity alone predicts? Or will it have done something that forces us to abandon every comfortable assumption about what we're really looking at? Before we dive deeper into this mystery, I need you to do something. If you're finding this fascinating, if your mind is already racing with possibilities, hit that like button right now. Subscribe to this channel so you don't miss what's coming next, because this story is developing in real time and the next few weeks could change everything. And tell me in the comments, where are you listening from? What time is it there? And here's the real question I want you to answer. Do you think we're looking at one object or multiple? Drop your thoughts below. And if you want to help this community grow, if you think more people need to hear about this, share this video on X, on Facebook, Reddit, or send it directly to someone who needs their mind blown. Thank you for having our back. Now, let's get into what's really happening up there. Let me take you back to October 2nd and walk you through exactly how this discovery unfolded. Stephen Burns wasn't some professional astronomer working at a major observatory. He was an amateur astrophotographer, someone who loves space enough to spend his free time processing the mountains of raw data that NASA makes publicly available from their rovers and spacecraft. On that particular day, he was working with images from Perseverance, the car-sized rover currently exploring an ancient crater on Mars. The rover had been instructed to photograph the night sky during a very specific window, the precise time when 3I/Atlas was predicted to pass closest to Mars. Now, closest is a relative term here. We're talking about 29 million kilometers of separation. That's roughly 75 times the distance between the Earth and our moon. At that range, you might think there would be nothing to see, maybe a faint smudge at best. But Burns had a technique. He took 9 minutes of consecutive images and stacked them into an animation, a method that reveals motion invisible in any single frame. When you do this with night sky photos, stars appear to move across the frame because of the planet's rotation, in this case, Mars spinning on its axis. Everything in the sky follows that predictable motion, creating neat parallel trails as the hours pass. Except for one thing. Something was cutting across that orderly motion at a completely different angle, moving at a speed that made absolutely no sense for a background star or any known object that should be in that region of space. Burns measured it. 60 kilometers per second. Let me put that in perspective for you. Earth orbits the Sun at about 30 kilometers per second, and we're absolutely flying through space at that speed. The Parker Solar Probe, humanity's fastest spacecraft, only reaches 192 kilometers per second at its very closest approach to the Sun, when solar gravity has accelerated it to maximum velocity. But 3I/Atlas maintains this blistering pace of 60 kilometers per second throughout its entire journey through our solar system. This thing is moving fast. Burns did what any excited space enthusiast would do. He posted his animation online. Within hours, the amateur astronomy community was buzzing. Other observers started downloading the same raw NASA images and running their own analyses. And that's when someone using the German username Nachtaf, which translates to night monkey, made a claim that sent ripples through the entire observing community. In the pictures from October 3rd, Nachtaf wrote, "You can see multiple comets. Not one object. Multiple." Another user named Alexander Plum pointed out something else that nobody could explain. At exactly 3 seconds into Burns's animation, there's a brief flash of green light. Go back and watch it frame by frame if you can find the footage online, and you'll see it. A diffuse glow, localized but distinct, appearing for just a moment before fading back into darkness. Now, this isn't a camera artifact. Those show up as single bright pixels, sharp and geometric. This isn't a cosmic ray hit which would leave a straight line streak. This is something else. A green luminosity in space. Here's where the chemistry gets weird. Green light in space has very specific causes. On Earth, we associate green with auroras, those beautiful curtains of light near the poles caused by solar particles hitting oxygen in our atmosphere. We see green in copper burning at high temperatures. Some bioluminescent organisms produce green light through chemical reactions. But in space, when comets glow green, it's almost always because of a molecule called dicarbon, 2 carbon atoms bonded together. When sunlight excites these molecules in a comet's atmosphere, they emit that characteristic green color. So naturally, when ground-based telescopes in Chile, specifically the European Very Large Telescope, performed spectroscopic analysis on 3I/Atlas in early September, astronomers expected to find large quantities of dicarbon. Spectroscopy is essentially reading the chemical fingerprint of an object by splitting its light into a rainbow and looking for the dark or bright lines that specific elements and molecules create. It's one of the most reliable tools we have for understanding what distant objects are made of. The results came back clear. 3I/Atlas showed virtually no dicarbon. The object is what astronomers call carbon chain depleted. In plain language, it shouldn't be glowing green. It doesn't have the molecules necessary to produce that color. Yet photographs from multiple ground-based telescopes in early September clearly showed a green hue developing around the object. And now here's that same green flash appearing in the Mars images. Let me address the elephant in the room, the claim about multiple objects. This is where we move from solid observational data into more speculative territory, but it's speculation coming from people with actual telescopes and sophisticated image processing software, not from random internet trolls making things up. When you stabilize the star field in Burns's animation, when you account for Mars's rotation and lock the stars in place so you can see what's actually moving relative to the background, there appear to be at least one or two additional points of light moving at different velocities from the main object. Could these be imaging artifacts? Absolutely. Digital cameras, especially when you're stacking multiple exposures, can create phantom signals. Could they be background asteroids that just happen to be in the frame at the same time? Possibly, though the timing would be remarkably coincidental. Could they be separate fragments, smaller objects traveling alongside the main comet, or even debris that's broken off during its journey through space? That's the question nobody can definitively answer yet, and here's why that's so frustrating. NASA has the data to answer it. The Mars Reconnaissance Orbiter's HiRISE camera, that's the high-resolution imaging science experiment, observed 3I/Atlas on October 2nd between 1 and 4 in the morning Mars local time. HiRISE is an extraordinary piece of technology. When it's photographing the Martian surface from orbit, it can resolve features as small as 30 centimeters across. That's sharp enough to see individual boulders, to distinguish between different types of terrain, to spot changes on the surface over time. Now, when you point that same camera at an object 29 million kilometers away, obviously the resolution drops significantly. But even at that distance, HiRISE should achieve a resolution of about 30 kilometers per pixel. Recent estimates suggest 3I/Atlas has a nucleus somewhere between 5 and 10 kilometers across. That means it should appear as a bright cluster of pixels in the HiRISE images, small, but definitely detectable and measurable. More importantly, HiRISE would be able to distinguish between a single compact nucleus and a fragmented or multi-component object. If there are multiple pieces traveling together, if there's a companion object, if there's anything unusual about the structure, an elongated shape, signs of jets, evidence of different regions with different brightness, HiRISE would see it clearly. But that's not all. The European Space Agency had two spacecraft watching as well. The ExoMars Trace Gas Orbiter and Mars Express both captured observations on October 3rd, using instruments specifically designed to study atmospheric composition and surface features. These weren't casual snapshots. These were coordinated, pre-planned scientific observations designed to gather the highest resolution data ever obtained of an interstellar object passing through our solar system. The observation windows were calculated months in advance. The spacecraft were positioned optimally. The instruments were calibrated and ready. Everything was set up to give us unprecedented views of this visitor from beyond our solar system. So where are the images? NASA's official statement has been minimal and frustratingly vague. The Mars orbiters successfully conducted their observations. Data is being processed. Updates will be provided as analysis continues. That statement was released over 24 hours after the observations were completed. Now, in the world of space imaging, 24 hours is actually plenty of time to at least preview raw data, to do initial checks, to confirm that the observations worked and captured what they were supposed to capture. Mars orbiters routinely release surface images within hours of acquisition. The HiRISE website typically updates with new Mars photos every few days, sometimes even daily during active observation campaigns. Yet here we are, and nothing from the 3I/Atlas flyby has appeared in public databases. Some observers have noted that the United States government has been dealing with various administrative disruptions that have affected the release of scientific data across multiple agencies. Budget constraints, personnel issues, the usual bureaucratic friction that can slow things down. But here's the thing, ESA operates completely independently. They have different funding sources, different administrative chains, different political oversight. They're a European consortium that doesn't answer to the American government. Yet their images haven't appeared either. The silence feels deliberate. And when official channels go quiet like this, amateur observers start talking, start speculating, start sharing their own findings through informal networks. Because here's what we know for certain, based on publicly available information that anyone can verify. The Perseverance rover absolutely captured something in those October images. Multiple amateur analysts examining the same raw data that NASA posted to their public archive are seeing anomalies. The object, or objects, moved at velocities consistent with 3I/Atlas's predicted motion. And there's that green flash that no one can explain with conventional comet chemistry. What we don't know is whether those apparent multiple objects are real physical bodies or processing artifacts. We don't know whether they're gravitationally bound to the main comet or just happen to be passing through the same region of space. We don't know what NASA and ESA scientists saw with their far more powerful instruments. And that not knowing is what makes this silence so significant. The October 3rd flyby represented the closest any operational spacecraft has ever come to an active interstellar object. Think about what that means. Since we've been capable of space exploration, we've only definitively identified 3 interstellar visitors. The first was 1I/Oumuamua, discovered in 2017, an elongated object that tumbled through the inner solar system, showed slight non-gravitational acceleration, and left before we could study it in detail. The second was 2I/Borisov, discovered in 2019, which looked and behaved much more like a typical comet, with a clear coma and tail following predictable physics. And now 3I/Atlas, discovered in July 2024, which is breaking rules in ways that make Oumuamua look normal by comparison. This was our chance, perhaps our only chance for decades, to understand what 3I/Atlas really is, to see its structure up close, to determine if it's a natural comet behaving strangely or something that requires a completely different explanation, to measure its composition directly instead of inferring it from distant spectroscopy, to watch how it responds to solar heating in real time. And as we wait for answers that may or may not come, the object itself continues its relentless journey toward the sun. Right now, at this very moment, 3I/Atlas is moving deeper into the inner solar system where Earth-based telescopes progressively lose sight of it against the overwhelming brightness of solar glare. By late October, it will pass behind the sun from our perspective, entering what astronomers call a solar occultation. Completely hidden from view, this blackout period will last for weeks, maybe a full month. During that time, while it's invisible to us, 3I/Atlas will experience the most intense heating of its entire journey. It will reach perihelion, the closest point to the sun in its orbit, on October 29th at a distance of roughly 1.02 astronomical units. That's just slightly farther from the sun than Earth is, well inside the orbit of Mars. When it emerges in November or December, it will either confirm every natural explanation we've been trying to construct, showing normal comet behavior, brightening from increased activity, maybe fragmenting if thermal stress cracks the nucleus apart, or it will have done something that comets simply don't do. And if that happens, if it emerges having changed in ways that gravity and ice sublimation can't explain, then every question we've been asking shifts. We move from "what kind of unusual comet is this?" to much more uncomfortable territory. But I'm getting ahead of myself. Before 3I/Atlas vanishes behind the sun, before we lose our ability to track it, we need to talk about what these Mars observations were really designed to detect. We need to understand why the timing of this data silence matters more than you might think. And we need to examine a pattern in how space agencies handle observations that produce unexpected results. If you're still with me, if you're following this mystery down the rabbit hole, do me a favor. Make sure you've subscribed to this channel. Turn on notifications, because what happens over the next few weeks could be one of the most significant developments in astronomy in our lifetimes, and I'll be covering every update as it breaks. The story you're hearing right now is based on information available as of early October 2024. But this is a developing situation. New data could appear tomorrow. New observations could change everything. and I want you here when it happens. Now, let's talk about the Mars blackout and what it might actually mean. There's a standard rhythm, a predictable pattern, to how space agencies communicate their discoveries to the public. When a spacecraft captures routine observations, images of a planet's surface, atmospheric data, measurements of magnetic fields, the data appears quickly. Within hours, sometimes within a single day, raw images populate public databases. Science teams draft press releases. Principal investigators give interviews to journalists. Social media accounts managed by NASA or ESA share highlights with millions of followers. The entire process is designed to be transparent, to build public interest and support, to justify the billions of dollars in taxpayer funding that make these missions possible. When that rhythm breaks, when the normal flow of information suddenly stops, people notice. Scientists notice first, the researchers who depend on this data for their work, who check the archives daily expecting new observations to appear. Then journalists notice, especially those who cover space exploration regularly and know what the usual timelines look like. And eventually, the public notices when expected announcements don't materialize, when questions posted on official forums go unanswered, when the excitement of a major observation fades into an uncomfortable silence. The technical explanation for delays centers on data processing pipelines and calibration requirements, and to be fair, these are legitimate considerations. Mars orbiters don't transmit images to Earth in real time like a live video feed. They store observations onboard in memory systems, then beam them back to Earth during scheduled communication windows using high-gain antennas pointed at our planet. From there, the data moves through various processing stages. Engineers apply geometric corrections to account for the spacecraft's motion during the exposure. They perform radiometric calibration to convert raw detector readings into meaningful brightness values. They filter out noise, cosmic ray hits, and instrumental artifacts. For a typical Mars surface observation, let's say high-rise photographing a crater or a canyon, this processing takes 6 to 12 hours from the moment the data arrives at the receiving station on Earth to when the calibrated image becomes publicly available. For a moving target against the star field, for something like observing 3I/Atlas where you're tracking an object instead of pointing at a fixed location on the planet, you might need additional processing steps. Maybe double that time, maybe 24 hours. Reasonable. Understandable. We're now well past 48 hours since the October 3rd observations. We're into day 3, day 4, and nothing has appeared. No raw images, no preliminary data, no update beyond that initial vague statement about ongoing processing. But there's another factor at play here, one that doesn't get mentioned in official statements but filters through the network of researchers who depend on NASA data for their professional work. In recent years, budget constraints combined with administrative disruptions have created bottlenecks in data release protocols. Not a formal shutdown, not an official hold, but the kind of bureaucratic friction that turns routine processes into delayed ones. Staff working reduced hours because positions weren't filled when people retired. Priority systems getting reshuffled as political appointees change the emphasis of different programs. Review chains lengthening as extra approval steps get added for sensitive observations or discoveries that might generate significant public attention. None of this is conspiracy. It's just the reality of how large government organizations function when they're under resource pressure and political scrutiny. But it doesn't fully explain why ESA has also gone silent. The European Space Agency operates under completely different administrative structures from NASA. They have different funding mechanisms, contributions from member states rather than annual appropriations from a single government. They have different leadership chains, different public communication requirements, different scientific priorities. When both agencies go silent simultaneously on the same target, it suggests some form of coordination. Scientists from both sides talking to each other, agreeing to wait until all data has been analyzed before making public statements. This kind of coordination happens, and it's not inherently sinister. When observations are complex, when preliminary results might be easily misinterpreted without proper context, it makes sense for research teams to hold back until they can present a complete picture. The problem is that this approach, however well-intentioned, creates an information vacuum. And that vacuum gets filled with speculation, with amateur analyses of varying quality, with theories that range from plausible to wildly imaginative. The silence from Simeon Schmusser adds another layer to this puzzle. Schmusser is an astrophotographer with a solid reputation in the amateur community for his ability to process difficult planetary data. He specializes in taking noisy, low-quality images and extracting subtle details that initial processing might miss. He's not someone who makes careless claims or seeks attention with false discoveries. On October 1st, a day before Stephen Burns's analysis of the October 2nd images, Perseverance captured another series of night sky photos. These were posted to NASA's raw image database within hours, following standard protocol. Schmusser downloaded them, applied his processing techniques, likely involving image stacking, noise reduction, contrast enhancement, and claimed to see an early glimpse of 3I/Atlas in those frames. If legitimate, this would mean the comet was detectable even before the main observation window, visible in images taken when it was slightly farther from Mars and presumably fainter. The claim hasn't been independently verified by professional astronomers, and to be honest, the object would have been extremely faint at that distance and geometry. But Schmusser noted something else in his initial posts. The motion he detected didn't perfectly match the predicted trajectory. Close, definitely consistent with 3I/Atlas, but with a slight deviation that he couldn't immediately explain. He posted his findings on social media platforms where the space observation community congregates, stating that more analysis was needed, but that the preliminary results were intriguing. He mentioned planning to do additional work to refine his measurements, to see if the apparent trajectory deviation was real or an artifact of his processing methods. And then he went quiet. No follow-up posts. No corrections or clarifications. No further discussion of what he found. Just silence. When an amateur astronomer goes quiet after making an intriguing claim, it usually means one of two things. Either they found an error in their analysis and are embarrassed about having posted prematurely, or they found something significant and are now preparing a more detailed, careful presentation, maybe even coordinating with professional astronomers to verify the results before going public again. Schmusser hasn't retracted his observations. He hasn't posted a correction saying, "I made a mistake. It was actually just noise," or "I misidentified a background star." He simply stopped commenting. That's interesting. Meanwhile, amateur astronomers around the world continue working with whatever data is available. The publicly posted Perseverance images from those crucial October nights remain accessible in NASA's raw data archive. Anyone with the right software, freely available programs like ISIS or commercial tools like PixInsight, can download these images, stack them, apply their own processing, and look for moving objects. Multiple independent analysts have now reproduced Stephen Burns's core finding. They confirm that there is at least one fast-moving object in those frames, moving at a velocity and direction consistent with 3I/Atlas's predicted motion. That part isn't controversial. The debate focuses on whether additional objects are present in the data. Some analysts see them clearly, distinct points of light moving at different rates or angles from the primary object. Others attribute these apparent additional lights to artifacts created by the stacking algorithms, to cosmic ray hits that coincidentally appeared near the comet's path in multiple frames, or to faint background asteroids that happen to be in the field of view. Without the high-resolution data from HiRISE and the ESA orbiters, without official confirmation or careful analysis using professional-grade tools and techniques, the question hangs unresolved in this uncomfortable limbo. What we're seeing here is a pattern that's become familiar in the age of open data and citizen science. Official channels constrained by review processes institutional caution, and bureaucratic friction. Amateur observers filling the information gap with varying degrees of rigor and reliability. And an object at the center of attention that continues generating more questions than answers. Let me lay out for you what we still don't know about 3I/Atlas despite months of observations by ground-based telescopes and space-based instruments. We don't know the exact size of its nucleus. Estimates currently range from less than 1 kilometer to more than 10 kilometers across, depending on assumptions about its albedo, how reflective its surface is, and whether what we're seeing in images is primarily the solid nucleus or an extended dust cloud surrounding it. That's an enormous range of uncertainty. The difference between 1 kilometer and 10 kilometers is a factor of 1,000 in volume, 1,000 in mass if the density is similar throughout. We don't know its rotation rate with any confidence. Some observations have suggested rapid rotation, maybe a spin period of a few hours. Others show no clear periodicity in the brightness variations. Understanding how fast it's spinning tells us crucial things about its structural integrity, whether it's a single solid body that can hold together under centrifugal forces or a loose aggregate of smaller pieces barely held together by weak gravity. We don't know where the outgassing is coming from. Is material venting from discrete jets at specific locations on the nucleus, like we've observed on comets such as 67P/Churyumov-Gerasimenko that the European Rosetta mission studied up close? Or is gas and dust escaping from broad areas of the surface in a more diffuse pattern? Discrete jets suggest localized deposits of volatile ices, possibly indicating that different regions of the nucleus have different compositions or different exposure histories. Broad, uniform emission suggests a more homogeneous surface composition. And perhaps most importantly for this entire mystery, we don't know the degree of fragmentation, if any. Has the nucleus split into multiple pieces at some point during its journey, either recently or in the distant past? Are there companion fragments traveling alongside the main body, pieces that broke off but remain gravitationally bound in a loose cluster? Or is the structure intact, a single solid object or rubble pile that has held together despite the thermal stresses and tidal forces it's experienced? These are fundamental questions, basic properties that we would know with certainty if we had been able to study this object up close. And these are exactly the questions that the Mars observations were supposed to answer. High-rise at 30-kilometer resolution should easily distinguish between a single compact object and a fragmented or multi-component system. Even if the pieces are separated by just a few tens of kilometers, close enough to appear as a single blur in ground-based telescopes, they should be resolved as distinct entities in high-rise images. The spectroscopic instruments on Mars Express and ExoMars Trace Gas Orbiter, specifically the Cassis camera and high-resolution stereo camera, should reveal regional composition variations if they exist. If one side of the nucleus is richer in water ice while another region is richer in carbon dioxide ice, those instruments would detect the difference through the colors and intensities of reflected sunlight. If there are distinct jets coming from specific locations, spectroscopy would show where different molecules are concentrated in the surrounding coma. The instruments functioned. We know this because both spacecraft continue operating normally, returning data from their primary missions studying Mars. The observations were executed according to plan. The spacecraft pointed where they were supposed to point. The exposures were taken during the predicted observation windows. The data was transmitted back to Earth and received by ground stations. All of that happened successfully. The data exists somewhere, sitting in archives at JPL in California, at ESA facilities in Europe, on hard drives and servers maintained by the science teams responsible for these instruments. We're just not seeing it. And that gap between what exists and what's been shared is what's driving all the speculation and concern. Now, let me be completely clear about something. There are innocent explanations for this delay. Data pipelines genuinely backed up by technical issues, maybe a problem with calibration files, maybe an unexpected glitch in processing software that needs to be fixed before images can be properly corrected. Scientists conducting thorough analysis before making statements, which is actually how science should work. You verify, you double-check, you make sure your findings are solid before you publish or announce them. Bureaucratic delays completely unrelated to the content of the observations. Paperwork stuck in review. Approvals waiting for someone who's on vacation. The mundane administrative friction that affects any large organization. These are all plausible, reasonable explanations that don't require anything unusual or sinister. But there are also less innocent explanations. Uncertainty about how to characterize unexpected findings. When you observe something you didn't expect, something that doesn't fit existing models, it takes time to figure out how to describe it accurately without either overstating or understating its significance. Consultation about whether preliminary observations warrant broader discussion before formal publication. When multiple institutions are involved, they sometimes agree to coordinate announcements rather than having different teams release potentially conflicting information at different times. Institutional hesitancy to make claims that might later require embarrassing retractions. Space agencies are extremely cautious about creating public excitement over discoveries that turn out to be instrumental artifacts or misinterpretations. There's a strong bias toward being conservative, toward waiting until you're absolutely certain before making bold statements. And then there are the concerning explanations, the ones that make scientists uncomfortable but that can't be entirely dismissed. Discovery of features that challenge comfortable assumptions about what comets should look like or how they should behave. Evidence of structures in the images, geometric patterns, surface features, signs of organization that don't fit into natural categories and would require careful language to describe without triggering premature speculation. Observations of behaviors that, if released without extensive context, would generate exactly the kind of speculation and public concern that agencies work very hard to avoid. I want to emphasize, we don't know which category applies here. That's precisely the problem. The absence of information creates this vacuum, and human nature fills that vacuum with speculation ranging from cautious to wild. What we can say with absolute certainty is that the next few weeks are going to matter enormously for how we understand this object and maybe for how we understand interstellar visitors in general. 3I/Atlas will emerge from behind the Sun in late November or early December, depending on how bright it becomes and how close to the Sun telescopes are willing to point. The moment it's visible again, ground-based observatories around the world will immediately start photographing it. Amateur astronomers will be watching. Professional facilities will have observation time allocated and scheduled. If it looks essentially the same as before, if its trajectory matches gravitational predictions within measurement uncertainties, if its brightness and spectral signature remain consistent with what we measured in August and September, then the natural comet explanation becomes significantly stronger. All the anomalies will still need explaining, but at least we'll know we're dealing with an object that follows predictable physics. If anything has changed, that's when things get really interesting. Evidence of maneuvering, any deviation from the gravitationally predicted path that can't be explained by outgassing thrust. Structural modifications visible in images, the nucleus looking different, having a different shape or brightness distribution. Unexpected brightening that exceeds what normal comet activity would produce at that solar distance. New compositional signatures in spectroscopy, different molecules appearing, ratios shifting in ways that thermal chemistry alone can't account for. Any of those observations would move this object into territory where natural explanations become increasingly strained. There's also the ESA's JUICE spacecraft to consider. JUICE is currently on its way to Jupiter, launched in 2023 on a mission that will eventually study Jupiter's large icy moons, particularly Ganymede. But right now, JUICE is in the inner solar system, and its trajectory happens to position it for potentially useful observations of 3I/Atlas. Between November 2nd and 25th, JUICE will be able to point its instruments at the comet just after perihelion, when it's emerging from the sun's glare but still experiencing peak activity levels from solar heating. JUICE carries high-resolution cameras, infrared spectrometers, and particle sensors designed to study planetary atmospheres and surfaces. These instruments weren't specifically designed for observing comets, but they're absolutely capable of gathering valuable data. JUICE is actually farther from 3I/Atlas than Mars was during the October flyby, but it has the significant advantage of observing during the most active phase of the comet's passage through the inner solar system. If the comet is going to do something unusual, if increased solar energy is going to trigger unexpected behavior, perihelion is when it would happen. The catch is that data from JUICE won't arrive quickly. The spacecraft is currently on the far side of the Sun from Earth, using its high-gain antenna as a heat shield to protect sensitive electronics from solar radiation. Communication is happening through a slower, lower-bandwidth backup system. So observations made in late November won't be downloaded and processed until sometime in February 2025 at the earliest. But they're coming eventually, and they'll show us what 3I/Atlas looked like at its closest, hottest point, from an angle and distance that no Earth-based telescope can match. Europa Clipper, another NASA spacecraft currently in transit to Jupiter, might also get observations depending on geometry and whether mission planners decide to allocate instrument time to this target. These spacecraft perspectives from different locations in the solar system, combined with resumed Earth-based observations once the comet emerges from solar occultation, will eventually give us a comprehensive picture. Eventually. But eventually isn't now. Right now we're in a gap between what's been observed by spacecraft around Mars and what's been shared with the scientific community and public. A gap between amateur discoveries, real signal mixed with possible artifacts, and official confirmation or correction. A gap between the questions being asked by researchers around the world and the answers that exist somewhere in data files we can't access. While we sit in that gap, 3I/Atlas continues its journey, approaching the sun, heating up, becoming more active, potentially doing things we won't know about until it reappears weeks from now and we finally see what changed during its time behind the veil. The frustration is palpable in the astronomy community. This is a once-in-a-decade opportunity, maybe once in a career for some researchers. Interstellar objects are phenomenally rare. We've only identified 3 with certainty in all of human history, despite searching for them systematically since telescope technology became good enough to detect them. The discovery rate suggests that at any given moment, there might be only a handful of these visitors passing through the inner solar system, and most of them are too faint or poorly positioned to be discovered before they're gone. 3I/Atlas was found early enough, bright enough, on a trajectory that brought it relatively close to Earth and Mars. It's been observable for months. We've had time to study it, to allocate telescope time, to coordinate international observations. This should be the triumph of modern astronomy: global cooperation, cutting-edge instruments, open data sharing producing comprehensive understanding of something we've never seen before. Instead, we have fragments, spectacular discoveries mixed with unanswered questions, data that exists but remains locked away, silence from official channels while amateur analysts argue about pixels and green flashes on internet forums. It's not how this was supposed to work. But here's what gives me hope, what keeps this story compelling despite the frustrations. Science has a way of forcing truth to the surface eventually. Data doesn't stay hidden forever. Too many people are watching, too many independent observers are gathering their own information. Too much pressure builds in the system for transparency to be denied indefinitely. Whatever NASA and ESA scientists saw in those Mars images will eventually be published. Whatever Simeon Schmusser found, he'll either share it or someone else will reproduce his analysis. Whatever 3I/Atlas does when it emerges from behind the sun, the entire astronomical community will document it from multiple angles with multiple instruments. The truth will come out. The question is just how long we have to wait and how much that truth will challenge our current understanding of what's possible. Before I continue, I want you to do something for me. If you're genuinely engaged with this story, if you want to understand what this object means for our place in the universe, leave a comment right now. Tell me, do you think the silence from NASA and ESA means they found something unexpected? Or do you think this is just normal bureaucratic delay? I'm genuinely curious what you think, and I read every comment. Also, make sure you've hit that like button. It genuinely helps more people discover this content, and more people need to be thinking about these questions. Now let's talk about something that's been public for months, but somehow hasn't gotten nearly the attention it deserves. The connection between 3I/Atlas and one of the most famous mysteries in the history of the search for extraterrestrial intelligence. August 15, 1977. Ohio State University. A radio telescope called Big Ear was conducting a routine survey of the sky, doing exactly what radio astronomers do night after night, listening to the cosmos, hoping to hear something besides natural radio noise. The telescope operated automatically, scanning narrow bands of frequencies and printing intensity readings on continuous paper, those old-fashioned rolls that fed through dot matrix printers and created permanent records that could be reviewed later. 3 days after this particular observation session, astronomer Jerry Emmon was reviewing the printouts when he noticed something that made him grab a red pen. A signal had appeared in the data, strong and narrowband, lasting exactly 72 seconds. The intensity was so far above background noise, so dramatically different from everything else on that page, that Emmons circled the alphanumeric sequence representing the signal strength and wrote one word in the margin. Wow! That single word gave the signal its name. For nearly 5 decades, the WOW signal has remained one of the most tantalizing unsolved mysteries in astronomy. Let me tell you why it was so significant and why it's never been explained. The signal came from the direction of Sagittarius, near a globular cluster designated M55, a dense ball of ancient stars orbiting in the halo of our galaxy. It was detected at a frequency of 1420 MHz, which sits right in the middle of what's called the water hole, a protected radio astronomy band where human transmissions are forbidden by international agreement specifically to allow the search for cosmic signals. Why 1420 MHz? Because that's the frequency where neutral hydrogen emits radio waves naturally. Hydrogen is the most abundant element in the universe. Any civilization advanced enough to build radio telescopes would know about the hydrogen line. It's one of the first things you discover when you study radio astronomy. For that reason, scientists searching for artificial signals have long argued that 1420 MHz is the obvious frequency for interstellar communication, the cosmic equivalent of a standardized channel where anyone listening would know to tune in. The WOW signal's bandwidth was extremely narrow, less than 10 kHz. Natural astronomical sources that produce radio emission, things like pulsars, magnetars, radio galaxies, create broadband signals spread across wide frequency ranges. A narrowband signal is exactly what you'd expect from an artificial transmitter, something designed and built with specific technical parameters. The signal's intensity rose smoothly, peaked, then declined symmetrically over exactly 72 seconds. That duration wasn't arbitrary. It was determined by how Big Ear's antenna system worked. The telescope used 2 feed horns separated in the sky, and as Earth's rotation swept them across the target, each horn had a window of 36 seconds. The signal appeared in both horns sequentially, which meant the source was transmitting continuously. Not a brief pulse, but a sustained broadcast lasting at least as long as the telescope could observe it. Follow-up observations found nothing. Big Ear was pointed back at the same region of sky repeatedly over the following weeks and months. Other radio telescopes were aimed at Sagittarius. No one ever detected the signal again. For decades, that's where the mystery sat. An extraordinary, unexplained detection that fit every criterion for an artificial signal except for the crucial one, repeatability. In science, if you can't reproduce an observation, if something happens once and never again, it becomes almost impossible to study or confirm. Then in 2024, Avi Loeb, a theoretical astrophysicist at Harvard and one of the most prominent and controversial voices in the search for technosignatures and extraterrestrial intelligence, decided to do a calculation that nobody had apparently done before. He traced backward the trajectory of 3I/Atlas and asked a simple question. Where was this object on August 15, 1977? Working from the comet's current position, velocity, and trajectory, accounting for the gravitational influences of the Sun and planets over nearly 5 decades, Loeb calculated where 3I/Atlas would have been on that specific date. The answer: approximately 600 astronomical units from Earth, far out in the outer reaches of the solar system, well beyond the orbit of Neptune, in the region where the solar wind begins to fade and true interstellar space begins. Now here's where it gets interesting. The WOW signal originated from sky coordinates of right ascension 19 hours 25 minutes, declination -27 degrees. Those are celestial coordinates like latitude and longitude but mapped onto the sky. Loeb calculated 3I/Atlas's position on August 15, 1977. The object would have been at right ascension 19 hours 21 minutes, declination -19 degrees. That's separated by about 4 degrees in right ascension and 8 degrees in declination. In angular terms on the sky, that's not identical, but it's remarkably close, about 9 degrees of total separation. Let me give you perspective on what 9 degrees means astronomically. The full moon appears about half a degree across in our sky. So 9 degrees is roughly 18 full moon widths, which sounds like a lot. But consider this: the entire sky contains 41,253 square degrees. The chance of 2 random directions in the sky aligning to within 9 degrees of each other purely by coincidence is about 0.6%. Not impossible, but unlikely enough to raise eyebrows. But alignment alone doesn't prove causation. Correlation isn't proof, as scientists correctly remind us constantly. Loeb went further. If 3I/Atlas actually transmitted the WOW signal, how powerful would the transmitter need to be to produce what Big Ear detected? The signal intensity measured between 54 and 212 Janskis. A Jansky is a unit measuring radio flux density, and for context, the strongest natural radio sources in the sky, like the Sun during solar storms or Jupiter's intense magnetosphere, typically measure in the hundreds to thousands of Janskis at specific frequencies. At a distance of 600 astronomical units, generating the received intensity would require a transmitter outputting between 0.5 gigawatt and 2 gigawatts of power. Let that sink in for a moment. A gigawatt is a billion watts. For comparison, a typical nuclear power reactor generates about 1 gigawatt of electrical power. So we're talking about the output range of 1 or 2 nuclear. 3I/Atlas is currently moving toward the Sun at approximately 60 kilometers per second. It's coming inbound on a hyperbolic trajectory, meaning it entered the solar system from interstellar space with enough velocity to eventually escape again, rather than being gravitationally captured into a closed orbit. When you account for Earth's motion around the Sun and the specific geometry in August 1977, where Earth was in its orbit, what direction it was moving, where the object was relative to us, the relative velocity would produce a blue shift. Loeb calculated the expected frequency shift based on the velocities involved. It's close to what Big Ear observed in the WOW signal, though not a perfect match. The difference could be explained by uncertainties in reconstructing the exact position and velocity vectors nearly 50 years later, or potentially by the signal having been transmitted in a specific direction using a focused beam rather than broadcast omnidirectionally like a lighthouse. Now here's where this gets strategically interesting from a communication standpoint. If you're an intelligence wanting to announce your presence, wanting to send a signal that anyone looking would recognize as potentially artificial, broadcasting near the hydrogen line makes perfect sense. As I mentioned, hydrogen is the most fundamental element, the most common in the universe, the building block of stars. The 21-centimeter hydrogen line is so fundamentally important to radio astronomy that any civilization capable of detecting radio waves would monitor that frequency. It's the universal calling card, the frequency where you'd listen if you wanted to hear from someone else. The fact that the WOW signal lasted 72 seconds is also significant in this context. That duration wasn't random. It was determined by the Big Ear telescope's design, as I explained earlier. But from the transmitter's perspective, this means the signal was broadcasting continuously throughout the entire time Big Ear could observe it. Not a brief pulse, not a 1-second blip, but a sustained transmission. If 3I/Atlas was responsible, this raises immediate questions that we can't yet answer but that are fascinating to contemplate. Was it a beacon? An automated signal announcing presence to anyone in range, the interstellar equivalent of a lighthouse or navigation marker? Was it a directional pulse aimed specifically at our solar system, timed for when the probe was at a certain distance? Was it an attempt at actual communication, encoding information in the signal structure that we simply lacked the sophistication to decode from a single 72-second observation? Or was the whole thing a coincidence? 3I/Atlas just happened to be aligned with a natural radio source we haven't identified, some pulsar or magnetar or other cosmic object that emitted a brief burst that looked artificial but wasn't. The problem is we don't have radio telescope data on 3I/Atlas. Not from August 1977, obviously, since the object hadn't been discovered yet. But also not from now. No observatory has reported pointing radio dishes at this object to search for emissions. The focus since its discovery in July 2024 has been entirely on optical observations, photography, spectroscopy, measuring its brightness and color. The questions being asked are about physical composition and structure, not about whether it's transmitting radio signals. Avi Loeb is arguing quite vocally that this needs to change immediately. The object is approaching perihelion, getting closer to the sun, which means higher temperatures, more energy available from solar heating. If there's any kind of technological system involved, if there are dormant systems that activate when power becomes available, this would be the time. If it transmitted once at 600 astronomical units when it was cold and distant, and if it's designed to transmit at specific points in its journey, perhaps when passing close to stars or planets, then right now as it enters the inner solar system would be the logical time to listen. Radio telescopes like the Very Large Array in New Mexico, facilities in Australia like Parkes Observatory, the vast arrays in China including FAST, the 500-meter aperture spherical telescope, even the successor facilities to Arecibo in Puerto Rico, all of these could monitor 3I/Atlas across multiple frequencies. Not just the hydrogen line, but across the entire radio spectrum where artificial signals might appear. The observation would be straightforward. Point the antenna. Listen for hours or days. Record everything. Compare the target's radio emission to background sky noise. Look for any narrowband signals, any modulation patterns, any repetitive structures or time-varying behavior that natural sources don't produce. If there's nothing, if 3I/Atlas is radio silent, fine. It costs a few hours or days of telescope time to rule out the hypothesis, and at least then we'd know. But if there's something, if this object is emitting even faint radio signals, even intermittent transmissions, that changes everything about how we interpret what we're looking at. Because here's the thing, comets don't broadcast. A chunk of ice and rock from another star system, no matter how unusual its chemistry, doesn't generate narrowband radio signals at specific meaningful frequencies. Natural astronomical sources certainly produce radio emission, pulsar spin and beam radiation like cosmic lighthouses. Magnetars have such intense magnetic fields that they generate radio bursts. Even planets like Jupiter produce radio noise from charged particles spiraling in their magnetospheres. But all of these natural sources are broadband or have characteristic signatures that we recognize. They're chaotic, lacking the structure that indicates intentional communication or technological origin. The WOW signal had structure. It had narrow bandwidth concentrated at a meaningful frequency. It appeared once, broadcast continuously for at least 72 seconds, then disappeared. And if Avi Loeb's 0.6% coincidence calculation is actually showing us causation rather than correlation, then somewhere in the outer solar system 48 years ago, something transmitted a signal powerful enough for a small radio telescope in Ohio to detect it clearly above background noise. That something is now racing past Mars, approaching the sun, hidden from our view, doing things that comets aren't supposed to do. The question isn't whether we should be listening for radio signals from 3I/Atlas. The question is why the hell aren't we already doing it? Why isn't there a coordinated international campaign with multiple radio observatories keeping constant watch on this object as it reaches its most active phase? The answer, frustratingly, comes down to resources and priorities. Telescope time is expensive and heavily competed for. Every hour spent observing something that might turn out to be a normal comet is an outlier, perhaps once in a career. Spending time on marginal hypotheses feels like a gamble when there are 100 other objects waiting for observation, projects with guaranteed science returns, questions that don't require defending extraordinary claims to peer review committees. But here's the counter-argument. If there's even a 1% chance that 3I/Atlas is transmitting, the payoff from detecting that signal would dwarf every other discovery combined. It would answer the most profound question humans have ever asked. Are we alone? 1% odds are terrible for a lottery ticket but transformative for existential questions. The cost of listening is measured in telescope hours. The cost of not listening, if Loeb is right, is measured in lost opportunity, potentially the only chance in our lifetimes to document active communication from an interstellar visitor. Some observatories have begun preliminary monitoring. The Allen Telescope Array in California, operated by the SETI Institute, has pointed dishes toward 3I/Atlas periodically since September. No signals have been reported publicly, but SETI protocols typically require extensive verification before announcing detections. A single observation showing something unusual gets logged, analyzed, and kept quiet until independent confirmation can be obtained. The 1977 WOW signal taught that lesson. One remarkable detection without repetition becomes a permanent mystery rather than actionable science. The Breakthrough Listen project, funded by Yuri Milner and based at UC Berkeley, has access to some of the world's most sensitive radio telescopes. They've been searching for technosignatures, evidence of technology beyond Earth, for years. 3I/Atlas would be an obvious target, fitting perfectly within their mission parameters. Whether they've observed it, what they might have found, remains undisclosed. These projects operate with deliberate caution, publishing results only when confidence is high. So we wait. We wait for official images from Mars. We wait for 3I/Atlas to emerge from behind the sun. We wait for radio observations to be completed, analyzed, and either reported or dismissed. And while we wait, the comet continues its journey, oblivious or perhaps acutely aware of all the attention focused on its frozen nucleus. Let's talk about what happens if Loeb is wrong. If December arrives and 3I/Atlas emerges looking exactly as predicted, following a purely gravitational path, showing normal post-perihelion brightening, with chemistry that turns out to have boring explanations. The nickel emissions get attributed to some exotic but natural process involving carbonyl chemistry. The forward jet is explained by asymmetric sublimation from a rapidly rotating nucleus. The chemical inversions trace back to formation conditions in a protoplanetary disk with unusual composition but nothing fundamentally impossible. The trajectory alignment with planets gets dismissed as selection bias. We notice interstellar objects when they pass close to something we're watching, so of course the ones we detect appear to target our neighborhood. The WOW signal correlation becomes just that, a correlation, a 0.6% coincidence that happened to occur but means nothing. The mass discrepancy gets resolved when better observations reveal the object is smaller than initial estimates suggested, or that our models of interstellar object populations were simply incomplete. All of these resolutions are plausible. Science is filled with mysteries that seemed profound until someone figured out the mundane explanation. Pulsars were briefly considered alien beacons until we understood they were rapidly spinning neutron stars. Fast radio bursts generated speculation about advanced civilizations until we traced them to magnetars and colliding neutron stars. The list goes on. If 3I/Atlas turns out to be natural, the story doesn't end. It becomes a valuable data point, the third interstellar object studied in detail, teaching us about the diversity of materials and processes in other solar systems. Every anomaly that gets explained adds to our understanding of comet chemistry, of how objects form around different types of stars, of what happens during billions of years adrift in interstellar space. That's worthwhile science even without the headline-grabbing implications of artificial origin. But let's talk about what happens if Loeb is right. If 3I/Atlas does something in December that can't be explained naturally. What would that look like specifically? The clearest sign would be maneuvering. If the object emerges from behind the sun on a trajectory that deviates from gravitational predictions by more than measurement uncertainty can account for, that's a smoking gun. Not subtle outgassing thrust that produces millimeters per day squared of acceleration. We're talking about velocity changes measured in kilometers per second, applied during the occultation period when we couldn't observe it. Changes large enough to redirect the trajectory toward Earth or Mars or some other target of interest. Calculating trajectories in space is extraordinarily precise. We can predict where planets will be centuries in advance to within kilometers. For an object like 3I/Atlas, with thousands of positional observations compiled over months, the gravitational trajectory is known with high confidence. Any significant deviation would be immediately obvious the moment telescopes reacquire it in November or December. Another clear sign would be structural changes that can't be explained by fragmentation or thermal stress. If the object looks geometrically regular in post-perihelion images, if it shows features suggestive of construction, flat surfaces, right angles, repeating patterns that would demand explanation. Natural objects can occasionally produce geometric features through crystallization or fracture patterns. But there are limits. A perfectly spherical object or a clearly cylindrical one would be hard to explain naturally. An object with visible components that appear modular or attached rather than gravitationally bound would raise immediate questions. Radio emissions remain the gold standard for proving artificial origin. If 3I/Atlas starts broadcasting narrowband signals, especially at meaningful frequencies like the hydrogen line, especially with any kind of modulation or information content, the debate ends. You can't fake that with natural processes. Comets don't generate coherent radio transmission. Even magnetized objects produce broadband noise, not narrowband carriers. Optical signaling is another possibility. If the object begins flashing or pulsing with regularity, if it changes brightness in ways that correlate with our orbital position, brightening when we're looking, dimming when we're not, that suggests intentional signaling. Comets vary in brightness as they rotate, as different regions of varying reflectivity rotate in and out of view. But those variations are smooth and periodic, locked to the rotation rate. Sudden changes, irregular patterns, or brightness modulations that seem responsive would be extraordinary. Then there's the question of what it might release. If objects separate from the main body after perihelion, if those objects follow trajectories that intersect with Earth or other planets, if they display independent maneuvering capability, we'd be watching a deployment. That scenario enters territory that most scientists are deeply uncomfortable discussing publicly because it sounds like science fiction, like Hollywood invasion narratives that have nothing to do with how real contact would likely unfold. But discomfort doesn't change physics. If an interstellar object has the capability to release smaller probes, and if those probes head toward Earth, we detect them. Our space surveillance networks track objects as small as 10 centimeters in low Earth orbit. Something entering our atmosphere or approaching our planet would be seen, photographed, and analyzed. The question then becomes not whether we'd notice, but how we'd respond. First contact protocols exist in theory. The SETI Post-Detection Task Group, part of the International Academy of Astronautics, has published guidelines for what should happen if we detect a confirmed signal from extraterrestrial intelligence. Verify the detection independently. Inform relevant authorities and scientific organizations. Avoid hasty public announcements until confidence is high. Coordinate international response through entities like the United Nations. But those protocols assume detection of a radio signal from light years away, something we can study at leisure with no immediate consequences. They don't really address what happens if the source is already here, already in our solar system, already approaching. The dynamics change completely when contact is imminent rather than theoretical. Governments would become involved immediately, not through conspiracy or cover-up, but through legitimate concerns about security, public safety, and international coordination. If an object of unknown origin and capability is approaching Earth, defense establishments need to assess threat level. Is it communicating? Is it responsive? Does it show any sign of hostility or just scientific curiosity? The scientific community would mobilize. Every major observatory would be watching. Space agencies would coordinate observations. Data would be shared in real time through networks designed for rapid response to transient astronomical events. The Minor Planet Center, the Central Bureau for Astronomical Telegrams, the Astronomer's Telegram, all the systems astronomers use to communicate discoveries would light up with reports. And the public would know almost immediately, not because of official announcements necessarily, but because amateur astronomers would be watching too. Thousands of people around the world with telescopes and cameras pointed at the sky, sharing what they see on social media, on forums, through live streams. In the age of global connectivity, keeping something like that quiet is functionally impossible. The economic impact Loeb mentioned, markets crashing, would stem not from the object itself posing danger but from radical uncertainty. Financial systems price risk based on models of how the world works. Discovering that we're not alone, that interstellar travel is possible, that something built by non-human intelligence is approaching our planet shatters those models. Every assumption about humanity's future, about our uniqueness, about our trajectory as a civilization, gets rewritten. Investment strategies predicated on certain technologies remaining dominant would collapse if we suddenly have evidence that far more advanced technology exists. National security frameworks built on terrestrial concerns would need immediate restructuring. Even basic questions like property rights, territorial sovereignty, and legal jurisdiction become complicated when dealing with non-human entities. This isn't catastrophizing. It's recognition that paradigm shifts have consequences. The Copernican revolution, discovering Earth orbits the Sun rather than being the center of everything, took generations to fully integrate into human thought. The discovery of the Americas by European explorers fundamentally restructured global civilization in ways both profound and tragic. First contact with non-human intelligence would be an event of equal or greater magnitude. But let's be clear about probabilities. The likelihood that 3I/Atlas will do something unambiguously artificial in December remains low. Most scientists would estimate it well below 10%, perhaps below 1%. The null hypothesis, that it's a natural comet with unusual but explicable properties, remains the most probable explanation by far. What makes this situation noteworthy isn't certainty but the combination of anomalies and opportunity. We have an interstellar object behaving strangely enough to warrant serious attention. We have specific, testable predictions about what might happen over the next few months. and we have the instruments and expertise to observe it thoroughly, to gather data that will either confirm the natural explanation or force us into radically new territory. This is how science works at its best. Someone proposes a hypothesis that sounds outlandish. Others don't dismiss it outright but instead ask, what observations would prove or disprove this? Then everyone goes and makes those observations. If the hypothesis fails, it gets discarded and we move on with refined understanding. If the hypothesis succeeds, our entire framework shifts. Avi Loeb has been willing to put his reputation on the line by publicly discussing the artificial hypothesis. Many of his colleagues privately criticize this, arguing that extraordinary claims require extraordinary evidence and that speculation without definitive proof does more harm than good. But Loeb counters that science progresses by exploring possibilities, not by prematurely ruling them out based on discomfort. The tension between these positions reflects a deeper philosophical question about how we do science when dealing with low-probability, high-impact scenarios. Do we wait for absolute proof before discussing possibilities? Or do we openly explore hypotheses that might seem unlikely but would be transformative if true? History suggests that both approaches have value but that progress often comes from those willing to challenge consensus. Plate tectonics was ridiculed for decades before becoming accepted geology. Meteorites were dismissed by the French Academy of Sciences as folklore until specimens could no longer be ignored. Every field has examples of ideas that seemed absurd until evidence accumulated past the point of deniability. 3I/Atlas sits in that uncomfortable space. Not absurd enough to dismiss entirely. Not every comet we've ever studied closely has been dominated by water ice. When the European Space Agency's Rosetta spacecraft spent 2 years alongside Comet 67P/Churyumov-Gerasimenko, instruments measured the volatiles outgassing from the nucleus in exquisite detail. Water made up roughly 80% of the gas by volume. Carbon dioxide contributed maybe 3 to 10% depending on the region of the nucleus. Carbon monoxide, methane, and other molecules appeared as trace constituents. This pattern holds across comets. Whether they formed in our solar system or, like 2I/Borisov, came from another star system, water dominates. This isn't arbitrary. It reflects the conditions in protoplanetary disks where comets form. Water ice condenses at temperatures around 150 Kelvin. In the outer regions of a forming solar system, beyond what's called the snow line, temperatures drop below that threshold and water ice becomes abundant. That ice gets incorporated into small bodies, comets, icy planetesimals, the building blocks of giant planets. Carbon dioxide ice forms at colder temperatures, typically below about 80 Kelvin. That means carbon dioxide doesn't condense until you're much farther from the star, well into the outer solar system equivalent regions. Objects forming between the water snowline and the carbon dioxide snowline should be water-rich with some carbon dioxide. Objects forming beyond both lines can incorporate significant carbon dioxide, but they'd still accumulate substantial water during the inward migration or gravitational perturbations that eventually send them careening through space. 3I/Atlas flips this completely. The James Webb Space Telescope spectroscopy shows carbon dioxide to water in an 8:1 ratio by number of molecules detected in the coma. By mass, it's even more dramatic because carbon dioxide is heavier than water molecule for molecule. The coma is roughly 87% carbon dioxide, 9% carbon monoxide, and a mere 4% water vapor. Martin Cordner, who led the Webb observations, proposed that the comet formed in a carbon dioxide-rich region of its parent protoplanetary disk. But even that explanation struggles because you'd need formation temperatures cold enough to condense carbon dioxide as the primary ice while somehow excluding water, which should condense first at warmer temperatures as the material migrated inward or as the disk evolved. Another hypothesis involves radiation processing over billions of years in interstellar space. Cosmic rays, high-energy particles streaming through the galaxy, could selectively break apart water molecules while leaving carbon dioxide intact. Laboratory experiments show that water ice bombarded with radiation does produce carbon dioxide through chemical reactions. You could potentially create a surface layer enriched in carbon dioxide through this process. But that should be a surface effect, limited to maybe the outer few centimeters or at most meters of the nucleus. Once the comet approaches the sun and starts shedding material through sublimation, you dig through that process layer relatively quickly. Within days or weeks of active outgassing, you'd expect to breach the radiation-damaged surface and start exposing fresh interior material that has the original composition, presumably water-rich like every other comet. The Webb observations were taken on August 6th, when the comet was about 2.5 astronomical units from the sun. At that distance, it had been active for weeks already. Dust and gas had been streaming off the nucleus continuously. Yet the chemistry showed no sign of transitioning to a water-dominated state. The carbon dioxide remained overwhelmingly dominant. If the entire nucleus is carbon dioxide-rich, not just the surface, then radiation processing can't explain it. You'd need the object to have formed with this chemistry intrinsically, which requires either an extremely unusual formation environment or processes we don't currently understand. There's one more possibility that researchers haven't widely discussed, but that fits the data uncomfortably well. What if the object isn't a comet in the traditional sense? What if it's something that was manufactured or processed, where the composition was chosen deliberately rather than inherited from natural formation? Industrial processes on Earth produce carbon dioxide. We extract it, compress it, use it for everything from carbonating beverages to supercritical fluid extraction to rocket propellant. A spacecraft using carbon dioxide as propellant or coolant, leaking or venting that material as it warms up near the sun, would show exactly this chemistry: carbon dioxide dominant, water minimal, other volatiles as trace contaminants. This is speculation, obviously. There's no direct evidence of technological origin. But when natural explanations require stacking unlikely conditions, formation in an exotic environment, billions of years of selective radiation processing that somehow affects the entire nucleus, chemistry that violates every pattern observed in other comets, the artificial hypothesis starts to seem less outlandish by comparison. The nickel-iron separation. Let's revisit the metal emissions because the details matter and they've been somewhat glossed over in popular coverage. When astronomers talk about detecting nickel and iron in a comet's coma, they're observing emission lines, specific wavelengths of light that atoms emit when excited by sunlight. The process works like this. Solar ultraviolet photons hit metal atoms in the coma. The photons have enough energy to knock electrons in the atom up to higher energy levels. When those electrons fall back down to their original levels, they emit light at characteristic wavelengths determined by the atom structure. Nickel produces a prominent emission line at 344.6 nanometers in the ultraviolet. Iron has multiple lines, with strong ones around 358 nanometers and 372 nanometers. Spectroscopy splits light into its component wavelengths, creating a spectrum where these lines appear as bright features against the background. By measuring the intensity of these lines, astronomers can calculate how many atoms are emitting, essentially how much nickel or iron is present in the coma. The European Very Large Telescope observed 3I/Atlas across multiple epochs between August and late September 2024. In the earliest observations, when the comet was about 3.1 astronomical units from the sun, they detected nickel emission clearly. They saw no iron. None. The iron lines were absent or below detection limits. As the comet moved closer and brightened, iron emission finally appeared once it passed about 2.6 astronomical units. But even then, the nickel-to-iron ratio was extreme, orders of magnitude higher than what any model of comet composition predicts. In solar system material, the sun, meteorites, most astronomical bodies, nickel and iron appear together in well-defined ratios. For every nickel atom, you typically find somewhere between 10 and 20 iron atoms. This ratio reflects how these elements formed in supernovae, how they condensed in the early solar system, how they exist in metal alloys and minerals. Nickel and iron behave similarly chemically. They have similar atomic masses. Nickel is atomic number 28, iron is 26. They alloy together easily, forming metal mixtures that are more common than pure nickel or pure iron in nature. In meteorites, nickel-iron alloys dominate the metal fraction. In Earth's core, iron is the primary element, but nickel is the major alloying component. When comets release metals, those metals come from dust grains embedded in the ice. The grains are microscopic fragments of material that condensed in the protoplanetary disk or in stellar outflows before being incorporated into the comet during formation. When heated, the grains release atoms that get carried into the coma by outgassing. The temperature required to vaporize nickel and iron from silicate grains or metal alloys is high, well over 1000 Kelvin. At 2.8 astronomical units from the Sun, surface temperatures on a comet nucleus reach maybe 200 to 250 Kelvin at most. That's nowhere near hot enough to vaporize refractory metals. So how is 3I/Atlas producing nickel and iron emissions at these distances? The leading hypothesis involves volatile metal compounds, specifically nickel tetracarbonyl, NiCO4. This is a molecule where a nickel atom is bonded to 4 carbon monoxide molecules. It's a gas at room temperature and decomposes under ultraviolet light, releasing free nickel atoms. Here's the thing about nickel tetracarbonyl: it doesn't form naturally in space. On Earth, we manufacture it industrially through the Mond process used to purify nickel from ores. You heat impure nickel with carbon monoxide gas at specific temperatures, around 50 to 60 degrees Celsius, and pressures. The nickel reacts to form nickel tetracarbonyl vapor. You then heat that vapor to higher temperatures, around 200 degrees Celsius, which causes it to decompose, depositing pure nickel. Could some natural process in a comet produce nickel tetracarbonyl? Possibly, if you have the right starting materials and conditions. You'd need metallic nickel particles in close contact with carbon monoxide at temperatures where the reaction is favorable. Over billions of years in interstellar space, with cosmic ray bombardment providing energy, perhaps such chemistry could occur. But you'd expect iron to undergo similar reactions. Iron pentacarbonyl, FeCO5, is another volatile metal compound, also used industrially, with similar formation conditions. If the comet is producing nickel tetracarbonyl naturally, it should also produce iron pentacarbonyl. Yet the observations show nickel without corresponding iron, suggesting that whatever process is releasing nickel is selective, favoring nickel over iron in ways that natural chemistry struggles to explain. The other possibility is that the nickel isn't coming from volatile compounds at all. Perhaps it's ablating from surface materials, coatings or structures that accumulated during the object's journey through interstellar space or that were present from the beginning. If the surface is enriched in nickel through some process we don't understand, solar heating could sublimate that nickel directly without requiring volatiles. Spacecraft that travel through space accumulate surface contamination from micrometeorite impacts and interstellar dust. Over millions or billions of years, this could build up layers with composition reflecting whatever regions of space the object traversed. If those regions happen to be rich in nickel dust, perhaps debris from specific types of supernova or stellar processes that produce nickel-rich ejecta, you might coat the object in nickel that then ablates when heated. Again, we're speculating to explain observations that don't fit standard comet models. Each explanation requires specific, somewhat unlikely conditions. And we still haven't addressed the forward jet. The anti-tail physics. Comet tails point away from the sun. This is so fundamental that it's one of the first facts taught in any astronomy course. But the reason is often simplified. It's not that the tail trails behind the comet as it moves. That's a common misconception. The tail points away from the sun regardless of which direction the comet is traveling because it's being pushed by solar radiation and the solar wind. There are actually two types of tails. Dust tails form from small solid particles lifted off the nucleus by sublimating gas. These particles are pushed by radiation pressure, the momentum of photons hitting them and imparting force. Dust tails are broad and curved because particles of different sizes respond differently to radiation pressure. Larger grains are pushed less and follow trajectories closer to the comet's orbit. Smaller grains are pushed harder and stream farther outward. Ion tails form from ionized gas, molecules that have lost electrons due to solar ultraviolet radiation. These ions interact with the solar wind, the stream of charged particles flowing outward from the sun. The solar wind drags ions along with it, creating a narrow, straight tail that points almost exactly radially away from the sun. Both types of tails point sunward because the forces, radiation pressure and solar wind, come from the sun and push material outward. This is so reliable that early astronomers used comet tails as indicators to understand the sun's influence beyond the visible disk. 3I/Atlas doesn't follow this rule. The Hubble images from July show a diffuse glow extending ahead of the nucleus, pointing toward the sun. The direction is opposite to what physics demands unless something else is happening. David Jewett's analysis of the brightness profile showed that light intensity drops off steeply with distance from the nucleus, much steeper than typical cometary coma. This suggests either the material is concentrated near the source or it's being removed rapidly after emission. One natural explanation involves perspective and geometry. Sometimes under specific viewing angles, we can see dust that's been left behind in a comet's orbit from previous passages. This orbital dust can appear to form a tail pointing forward from our perspective. But 3I/Atlas is on its first passage through the inner solar system. It's never been here before, so there's no old orbit trail of dust to see. Another explanation is active jetting from the sunward hemisphere. Imagine the nucleus spinning. As fresh areas rotate into sunlight, ice sublimates violently, creating jets of gas and dust that shoot outward from that side. If the sun-facing side is particularly active, dust could accumulate in a cloud in front of the comet before radiation pressure begins pushing it back. This requires substantial asymmetry. The day side needs to be far more active than the night side or the sides rotating into and out of sunlight. Such asymmetry is unusual but not unprecedented. Comet Hartley 2, visited by NASA's Deep Impact spacecraft, showed jets emanating primarily from the ends of its elongated nucleus. But Hartley 2 also had normal dust and ion tails extending away from the sun. The forward jets were additions to the normal structure, not replacements for it. 3I/Atlas shows the forward glow but no clear backward tail, at least not in the Hubble images. Ground-based observations from Chile have shown what might be a faint anti-tail extending opposite to the forward glow, but it's much fainter and less prominent than you'd expect for an object this active. Could the material be gas rather than dust? Gas doesn't form persistent tails because it disperses quickly. Molecules emitted from the nucleus expand outward, spreading and thinning until they're effectively invisible except very close to the source. A gas-dominated coma could explain the concentrated brightness near the nucleus and the lack of an extended tail. But if it's primarily gas creating the forward glow, what gas? Carbon dioxide and carbon monoxide, the dominant species in 3I/Atlas's coma, are transparent at visible wavelengths. They don't scatter sunlight efficiently. You wouldn't see a bright visible glow from those gases alone. You'd need dust mixed in, and dust should form a tail. This means observations made in November won't be fully downloaded until the spacecraft repositions in early 2025, likely February or March. So we'll see ground-based observations of 3I/Atlas emerging from perihelion in December. We'll get those results in real time. But the JUICE data, potentially the highest quality close-up observations of the comet at its most active, won't arrive for months after. That delay is frustrating but unavoidable given the spacecraft's trajectory and thermal constraints. Still, when the data does arrive, it will fill crucial gaps in our understanding of what the comet was doing during the period we couldn't observe it from Earth. The Galileo project watches. While space agencies track 3I/Atlas through telescopes and spacecraft, Avi Loeb's Galileo project is preparing for a different kind of observation. The project operates networks of sensors at multiple sites designed to detect and characterize unidentified aerial phenomena, UAPs. The motivation stems from a series of incidents involving U.S. military pilots reporting objects displaying flight characteristics beyond known aerospace capabilities. Some of these reports were declassified, generating public interest and congressional hearings. The Galileo project aims to bring scientific rigor to the field, replacing anecdote and blurry footage with calibrated instruments and open data. The probability remains high that natural explanations will prevail. That's how science usually works. The anomalies will resolve into exotic but ultimately mundane chemistry, unusual formation histories, statistical coincidences. And that's okay. Even if 3I/Atlas turns out to be just a weird comet, we'll have learned about the diversity of materials and processes in other solar systems, about how objects survive billions of years in interstellar space, about detection biases and population statistics. But there's also a non-zero chance, small but non-zero, that December brings confirmation of something that changes everything. And living in that uncertainty, watching the story unfold in real time, being part of the global community that's paying attention as these questions get answered, that's something special. So stay curious. Stay skeptical. Demand evidence but remain open to possibilities. And when 3I/Atlas reappears in the December sky, watch what happens. Because whatever we discover, whether it confirms our comfortable assumptions or shatters them, it will tell us something profound about the universe we inhabit and our place within it. If you've made it this far in this journey, you're part of something bigger. You've chosen to engage with questions that matter, to follow evidence into uncertainty, to think about what it means to search for truth in a universe that's stranger and more wonderful than we often imagine. Hit that subscribe button if you haven't already. Turn on notifications. Share this video with someone who needs to see it. And leave a comment telling me, what do you think 3I/Atlas really is? Natural comet with unusual properties? Something more? Drop your thoughts below. And if you made it all the way to the end, comment Atlas awaits so I know you were here for the full story. Thank you for watching. Thank you for thinking. And thank you for being part of a community that refuses to stop asking the biggest questions we can imagine. The universe is vast, mysterious, and waiting for us to understand it. Let's keep searching together.